We're ready to start this new demo organized within the framework of the ChEESE project. We will see, because I say a new one, because there have been two before and there will be another one. And today this is a live demo on the pilot demonstrator 2 on faster and real-time tsunami simulation, and applied to a use case on early warning that had been proposed by the IGN, Instituto Geográfico Nacional of Spain. The IGN is the institution on charge of the Spanish seismic network and the National Tsunami Warning System. And today we have with us here Juan Vicente Cantabella, the director of the Spanish seismic network, and also Beatriz Gaite, that will be presenting the problem proposed by the IGN, to our tsunami group in the ChEESE project. So first of all, I would like to welcome you all and say that thank you for being here, because first of all, we have done this in 3 days. We left 3 days for registering the people, so it was in a very short notice, and up to some minutes before the starting, we have more than 70 participants. And you see here that besides the organizers, let's say UMA, IGN, Chineca, and ChEESE partner, we have here all these NEAM TWS tsunami service providers in this region. We have also representative of the Aristotle project, and also institutions from Spain, but also from Europe. Here I also wrote down the names of partners of ChEESE, so I mentioned before, as HLRS or NGI. And finally, we have also colleagues from all over the world, in particular for the Americas, from the United States, Chile, Nicaragua, Ecuador, Costa Rica, Puerto Rico, Colombia, Mexico, Venezuela, and so another places like Lebanon or Israel. So thank you very much to you all to be here and to be so interested in this demo. And that has been delayed for a while, more than a month, because of this La Palma crisis that, the people of the AGN is well involved there. And we are lucky to have here today Beatriz, because the airport was closed during the weekend and she was there last week. So luckily we have Beatriz today with us here. And so the plan, as I said, is the same that you already received. And the idea is to keep this event as simple and as short as possible, and at the same time to try to avoid to be too rigid and close to the participation. We have included a discussion if you feel that we can have it at the very end. And probably it's a good idea that you can be writing the question or comment in the chat as they phrase and come to your minds. And some from us, from the UMA, from IGN, or any college in the tsunami team in ChEESE, can give a first answer in the chat. Carlos and I wouldn't be, because we will be quite busy, but any of these members can give an answer in the chat, and eventually we can come back to this question and comment at the very end of the demo. So this, after my introduction, Beatriz will be presenting the proposed problem by the IGN, and at the last presentation, I will come back describing the numerical setup of the problem that we are going to solve today. That will be the first part of the demo, and then at 16:30 we have a window in Chineca to start computing, and we will have resources at Marconi 10 at Chineca, and indeed we will have we requested just half an hour. At the end we have more time, but half an hour was enough for us, because in 15 minutes we should be able to perform all the simulation that we are proposing now. And also I would like to say that thanks to a November Christmas present that we received from Chineca on Friday afternoon, we will be able to do it in even less time, as we will describe later on. And as I said, at 16:30 we will start the live demo, where first the IGN will send us the file with all the parameters of the scenarios that we have to simulate, and then we will launch the simulation. We will start our chronometer and see how much it takes to perform all the simulation that we were presenting before. And at the same time that the results and the numerical results are coming out, Carlos will be presenting then. We will try to do as flexible as possible. And as I said, a discussion will follow if you think it is interesting. So I was saying that we have already another 2 demos from ChEESE project in the 4th and the 5th of November. And we will have another one, I think, the 30th of November in urgent seismic simulation. And let me have some words about the demo, the 5th of November, that World Tsunami Awareness Day on 2021. I think, in my personal opinion, will remain as a key date in computational tsunami science, as a real milestone and a step forward in the numerical simulation of tsunamis and high-performance computing was achieved. And let me briefly describe what ChEESE team, and in particular the INGV guys, performed that day. That was, in my opinion, really amazing. So they tried to perform a probabilistic tsunami forecasting exercise for the event of Samos 2020, and they performed nearly 40,000 simulations, in the computational domain that you see here in the figure, with a resolution of 30 arcseconds and a size for the problem of 2.6 million volumes. And the simulation time was 4 hours. Each of these simulations was taking 20 to 30 seconds. But the important thing is not the large number of simulations that they performed to do this PTF, but the time they took to perform all of them. And thanks to the huge computational resources of ChEESE provided 800 nodes, 800 nodes. That means 3,220 graphic cards. You can count, and they were able to do this 40,000 simulation in less than 10 minutes. Indeed, if you get your calculator and you take that you're doing in 30 seconds, that is the maximum time for the simulation, you will see that it's exactly 6 minutes for 40,000 simulations. So I just can say that in my humble opinion, this was a groundbreaking breakthrough, a major achievement of ChEESE project, and really amazing. So now we move to today exercise, a more modest and simple exercise, but it's not a challenge. As I was mentioning on the 5th of November, it's something that can be done, that is feasible today. And our example will consist in an event that takes place in the North Atlantic, with a major impact in Spain, Huelva, Cádiz, Canary Islands, and Galicia, but also Portugal and Morocco. A magnitude, I think, was 7.8 magnitude event. And we want, instead of producing a single deterministic simulation, we want to include some variability, but not, of course, performing a full PDF as we saw last 5th of November. And the uncertainty in the source definition will consider in hypocentric location, magnitude, strike angle, and deep angle, as probably Beatriz will be describing a little bit. That make a total amount of 135 scenarios that we want to perform to provide the alert levels, because that's the objective, to provide the alert level in this Spanish system, let's say. So we want to simulate the 135 scenarios, and we know that every of these scenarios can be performed in a single GPU, being faster than real time, but not only faster than real time, even more can be used in early warning, so in very few minutes. So let's say something that is below 5 minutes. And so our request to ChEESE to perform this still in early warning was, okay, if we can do with a single scenario in a single GPU, now we are going to request ChEESE 135 dedicated GPUs to perform this event. As you can see, it's something much more smaller than the one used in the PTF. Is the 4.2% of the resources used in the PTF demo. And as I said, is not a challenge that as the one we saw some days ago, but it's feasible with these entre small resources. Well, okay, the output of the simulation will be for each simulation the maximum wave height at the focal points and also arrival times. These focal points are provided by the IGN, and they are grouped by coastal segment, as we will see later. And you can see here the picture you have to the left. And we will use this segment to provide a alert level in each of these coastal segments. And the final output will be the maximum of the maximum or the maximum of the percentile 90 of the height at each of the focal forecast or focal points per coastal segment. So we will consider all the focal points in every of these segments that we have defined in the figure in colors. And for the arrival time, the minimum of the minimum arrival times on them. Of course, this numerical result could be used or can be used to posteriori to assess the sensibility of the result to varying just one parameter and leaving the other fixed, and also seeing if what we are doing makes sense or we can simplify things. And we must say that this is a very first test, and we didn't have the time to test them, to analyze the result. We just performed the event, and of course in real time here is for the very first time. So summing up and concluding, we are going to perform 150 simulations simultaneously, and then we are also going to use different computational domains and resolution, and then we will clustering the simulation in consecutive 135 simulations. Okay, I will explain that later in the setup description. And then we will be producing other messages that will be updated as simulation are coming with increased resolution or including new areas. The generation of this alert level will be done by coastal segments. Okay, and finally, to end with this first part, I would like to thank Seneca. They make everything really easy, really simple. And I mean, their support was really great. Also, I would like to mention at the very end that we have this Christmas present in November, and Chineke reserved for us not the 34 nodes that we are required, but the double. So instead of 135 GPUs, we are going to use 270, and later we will see which is the consequence of this gift. Okay, so that is the first part of our presentation. Now I give the floor to Beatriz to present the the setup that we have co-designed with IGN. So when you want.
Thank you, Jorge. I share my screen. Just tell me if you can see it.
Wait, I must. Okay.
Okay.
Let's see if you can. Okay, we see that. Yeah, perfect.
Okay. Thank you very much, Jorge. As Jorge explained, the Spanish Geographic Institute is the National Tsunami Warning Center in Spain, designated by IOC in 2015, and it emits alerts of tsunamis in Spain since that year. And it communicates to civil protection tsunami threats to Spanish coast. The outline of the tsunami warning alert is described in this slide, and is based on decision matrices and a scenario database of pre-computed scenarios to get the arrival time of the tsunami to the Spanish coast. simultaneously to the results of the decision matrix, where we run a tsunami simulation to get a more accurate result of the expected tsunami alert. This is an example of the automatic message we send to civil protection after 3 minutes an earthquake occurs and has a tsunami threat level. And as Jorge described, we discretize in the Spanish coast in several segments or areas, each one with a level of tsunami alert that corresponds to that segment. This is an example of the results we obtain with the real-time tsunami propagation simulations. We compute these simulations using 2 GPUs, NVIDIA V100, and it takes around 1 minute for earthquakes close to the coast in the Atlantic Ocean and also in the Mediterranean Ocean, around 5 minutes or more for earthquakes farther away from our coast, and also it depends on the bathymetric resolution we use. In order to compute these simulations, we do it only with one scenario that we take from the parameters of the closest fault that we have storage in a fault database, compiled from different scientific papers, also from the active fault database of the Geological and Mining Spanish Institute and some European projects as CERF. Using this fault database, we choose the closest fault to the earthquake hypocenter and take their fault parameters in order to compute the simulation. To get the size of the fault and also the slip, we use several magnitude scaling laws depending on the region that the earthquake has occurred, and also based on the mechanism of the fault. Here there is a summary of the magnitude size scaling relationships we use in these different areas. But as we consider only one scenario, we are not taking into account several uncertainties we have in earthquake location and the size of the earthquake. This is the reason for doing this demo of ChEESE project, in order to be able to simulate several scenarios to take into account these uncertainties, like, for example, the location of the hypocenter. We have an error on the location, but also we don't know which is the direction of rupture. To take into account the direction of the rupture and also the error in location, we have considered in this simulation one location in the center of the fault, in this case GC08, and 4 points with different locations depending on their location on the magnitude. So this doing this, we consider differences on X and Y axis of around 20 to 32 kilometers. We consider also differences in magnitude of 0.2, uncertainties on the strike angle of 15, degrees and also in deep of plus minus 20 degrees. These are the scenarios we are considering today and computing in Seneca supercomputing resources. Doing this, we would like to have a better estimation of the uncertainties we have and the dependence of the tsunami alert level we are obtaining when sending to civil protection a message with the different tsunami alert levels around all codes. Thank you.
Thank you, Beatriz, for your presentations. Okay, so now we go with the third one, where I will be presenting. Let's go here. I will be presenting. Let me know if you see my presentation now. Yep. But remember that to admit people from the if arriving. Okay, so I must say that we have 5 minutes to 16:30, but I'm not going to be very quick because we have tested in the very few minutes where I was presenting, and there is some problem with the setup that the Chineca prepared. So I won't go so fast because to give some time to Piero to try to fix the bug with the queue. So let's go with the third part of this, the introduction to the live demo, and where I will talk about the setup that we have used. First, some preliminary comment that, as you may know, many of you may know that tsunami early warning system, at least in the NEAM region, currently works with decision matrices and pre-computed databases. And since 2014, our group at the University of Malaga, we are proposing using simulation on the flight. And I mean, always we have done this in very tight collaboration with the INGV. And in 2018, we were awarded with the NVIDIA Global Impact Award that I mean, the award was just for proposing faster than real-time simulation in real time and just doing a single simulation in several GPUs at the time were like something like 10 or 10 or 12 of the GPUs that we are using at the time. And in this 2014, we were proposed with a Mediterranean challenge by the INGV that was like our flagship example that we were presenting everywhere, and perhaps some of you or many of you have heard us talking about this. But now we have given a huge step forward because now we are facing to include some uncertainty. We have seen that what we did in the 5th of November is something that is far away from this 2018 NVIDIA Global Impact Award that was doing a single simulation really fast in many GPUs. Now we are not using many GPUs. We are using just one GPU for a single simulation. And here you see the number that we were having for this problem, this Mediterranean challenge, that the idea was to solve a problem with 10 million volumes and with a 30 arsec resolution in all the Mediterranean, a simulation of 8 hours. So at that time, the idea was to do in less than 6 minutes, and we achieved that in 2014 with 10 NVIDIA Titan Black graphic cards that have the technology. The number 2012 is the technology that they were using. In that, the NVIDIA technology in that case was Kepler 2012. And with that, we did in nearly 6 minutes, in less than 6 minutes. And then we improved the code, the efficiency, and so on. And in 2017, with the same architecture, Kepler 2012, we were able to do in 4 minutes and something. But then new technologies arrived: the Pascal P100, the Volta V100, and the Ampere 100, and from 2016, 2018, and 2020. And you see how the computational times have evolved. With two P100, we were doing the simulation of this Mediterranean challenge in 4 minutes. With just one V100, we were doing in less than 5 minutes. And now with the new A100, we are performing in 3.5 minutes with a single GPU. So one single GPU now it's able to perform a single simulation of this size, and that is in the the time that is really good for this early warning. So if and keep this in mind, because that is important, because at the end we want to perform every of our scenario of our simulation in a single GPU. So the aim of the problem that we are posed is to provide alert levels given a tsunami event in the northeastern Atlantic, with impact, as I said, in Spain, Portugal, and Morocco. And as we are dealing with the Spanish National Tsunami Warning System, the domain that you see here on your left in red is the ATL, the Atlantic domain. Seems appropriate for this tsunami warning system, for the Spanish tsunami warning system. But we question ourselves about what would happen with another domains or another numerical resolutions. What will be the computing times for all that, in order to make our choice for computational domains. And then we consider a smaller domain for the Gulf of Cadiz in yellow here, but excluding the Canary Island and northern Spain. But it's the one we usually use when we are studying this kind of tsunamis in this area. Then we consider down in green, but down in the figure, one that is the Gulf of Cadiz, the Gulf of Cadiz and Canary Island, that was excluding northern Spain, but including the Canary Island. And finally, we consider a fourth domain that is including the Gulf of Cadiz and northern Spain. Okay, so we have considered these four domains, and now we are questioning about which are the computational times and the resolution that we can use in each of these domains. So we take the first one, the whole domain, the Atlantic one, and we see if that we have 1.5 or 30 arcsec resolution. We are doing in 1 minute. If we are using a coarse resolution, then it's nothing. It's 8 seconds the time required. And if we use a quarter of a minute or even less, an eighth of a minute, then the simulation is a bit too long, 7 minutes, and here already 1 hour. So for this first domain, we choose the 1 minute resolution. That is, as I said, a 30 arc-second resolution, 1.5 minute. We consider the second domain, and we have considered an enhanced resolution. Okay, we want to obtain a better simulation with an enhanced resolution of 1/4, and that's 3 minutes is okay. 28 minutes, if you want to do better, is too long. So we choose this resolution for this second domain. Then for the third domain, the Gulf of Cadiz and the northern Spain, again, if we use 7 million volumes, we are in 3 minutes. It's okay. If we multiply by 2 the resolution, we go to a 30 million problem, 30 million volume problem, and 21 minutes. So it's too much, too long. We must skip the 1/4 of a minute as resolution. And finally, for the smaller domain, we can go to an enhanced resolution of 1/8 and be performing the simulation in nearly 7 minutes. I haven't said that it's all performing Tesla V100, and for a simulation of 4 hours, that it should be enough to capture the main wave. Okay, so as I was saying, and Bea mentioned, the magnitude of the event, it's 7.8 with some variability, and we are going to vary, as I mentioned before, hypocenter location, magnitude, strike, and deep angle, and we're including this variability varying the UCADA model parameters, summing up a total of 135 scenarios, but multiplied by 4 domains. So today we are going to perform 540 simulations. Okay. Well, now how we are going to perform this? Well, in case everything works, that we don't know at the time being, we don't know. If we have these 135 GPUs, the only thing we can do, is to perform one after the other set of simulations. So 135 simulation for the Atlantic in 1 minute, then obtaining
sorry, Jorge, I'm Piero.
Yeah, Piero, tell me.
Nice to see you. Sorry, as already mentioned that we need to interact with Carlos directly because there is some problem with the script. I mean, because yeah, you know, there is something maybe weird in the configuration of the script, and because the reservation is up and running. So from Chineka side, all seems to be activated correctly. So I suggest to interact directly with Carlos. Carlos,
Yeah,
the man in charge for the So
yeah.
Basically, okay.
Okay, I can call you by Skype if you want. And...
Yeah, Carlo. I mean, yeah, it's faster than trying to interact by email. Yeah, okay. Sorry for interrupt, Jorge. Yeah.
Thank you very much, because the important thing here is the live demo, and it's in danger now. Yeah. Okay, please go ahead with this the Skype thing. Okay. Okay, so as I was saying, with the first allocation of resources, with these 135 GPUs, at the end, the only possibility is to perform this set of 135 simulation per domain, one after the other. And then at the end, if you are summing up the computational times required for every of these simulation, at the end we will be finishing in something like 14 minutes, obtaining first let's say a more rough estimation in the whole computational domain, and also for all the coastal areas in Spain. Then a second more refined estimation for the Gulf of Cadiz and also the Canary Island. Then and also an enhanced simulation for the northern Spain. And finally, in the closer area and the more exposed area, then a really much finer resolution simulation. And the question at the end would be, well, is it worthy or not? It's something that we should see. Okay, something has okay, thank you. And finally the second possibility, now that we have double the resources, we can do the same in 7 minutes 15 seconds, because what we will do was to use the first set of GPUs for doing the three first set of simulation. So here I add in the time and reserving the other set of 135 GPUs for performing the longest one, the one in the higher resolution numerical resolution. Okay, so as I said, the output were already described. Okay, so the output variables are, as I said, the maximum wave height and the arrival times. Okay, I already mentioned all that, so I can skip this. And finally, concluding again, but now just changing the numbers, because here we are going to consider 270 simulations that are going to be running at every time simultaneously in cluster of 135, and will be producing successive alert level in new regions or with increased resolution. And at the end, we will obtain an alert level map corresponding to the maximum of the maximum, or the maximum of the percentile 19 for the height, and for the minimum arrival times. So let's see, because the moment of the truth have arrived, and I don't think it's working properly, the system. But we will try to see if in 1 minute we have a first rough estimation in all coastal areas we are interested in for these alert levels. And then we will see if 3 minutes later we will have a refined estimation for Huelva and Cadiz and the Canary Island. We may ask ourselves if these alerts are modified or not, if it's worth it to do this or not. Okay, that's something that we have to analyze afterwards, and we didn't have the time yet. And finally, if in 7 minutes we will have an enhanced resolution simulation for Huelva and Cadiz, and at the same time refined estimation for northern Spain, as at this 7 minutes we will have the two last outputs of the two last cluster of simulation. So please cross your finger and let's try to proceed, because we are going to try to see if the live demo starts. So okay, by the time I will be asking to Bear or IGN guys to send us by email the full list of scenarios in the format already agreed.
Okay,
And the thing is, this part of obviously this part of the workflow is the part that should be automatized for a real event. In analogy, what we are currently doing in the Aristotle project, that from the SPADA system we receive the parameters, and the simulation is automatically run in here at the University of Malaga. And of course, the mathematician, we are never on shift. All this is done automatically, and once the results are obtained, this information is sent back to INGV in Rome. So this is the part that we are going to do by hand. And once that Carlos received this list of scenario, the demo is in his hand. Okay, yeah, Andre.
There's some question, yeah.
Yeah, I hear you. Here.
Jorge, you have showed this performance for different resolutions in different domains.
Yeah.
And I've noticed that in the two domains, for the same number of finite volumes, you had very different performance.
That may happen. Yeah, because you have the wet area is different. So it's you're not let's say consuming the same resources, even if you have the same number of volumes, if you have more or less water. And at the same time, if you have much more water, in the case you use several GPUs, that could be another possibility to use several GPUs for a single scenario in order to speed up. But then you have you lose something because of the scalability. Then the problem with many wet cells, they scale better. But the reason is that the different number of cells where do you really compute, because we are counting all the cells, all the cells in the domain. Okay, thank you for your question. Okay, Carlos, I see you a sad face after this disappointing thing. Yeah. Please try to.
Okay. So sorry
we can do it when we solve this problem, like recording the real thing in the live demo, and we can share with all the participants to see that we are not inventing, and really we can compute in that time. So please cheer up, and the floor is yours.
Let's try it with the live demo. Okay. So let me share my screen now. Okay. Do you see my screen now? Yes. Okay. Well, I'm going to try to support my, let's say, my on-the-fly session with this kind of poster on the right side, in which I summarize the workflow of this live demo, and on the left side I have the terminal in which I'm going to try to run the commands to perform all the simulation and obtain the results. As Jorge has described, the first part of this live demo, the one that involves IGN, is the setup. We consider an event in the Gulf of Cadiz. We consider different domains and resolution, not only the coarset one and the finest one, but also intermediate resolution domains in order to include more accurate response in the areas of interest. And then the IGN considers a variability on the Okada parameters and provide us a file, a text file with the list of the event to simulate. I have seen in my mail that Bea is already shared the events. Okay. So I upload to the machine, And let me show you this file. Okay, so we had a first field with a tag with the identifier of the event, let's say, and the parameters needed as input for tsunami high sea or Okada event. In this case, if we can count the lines, we can see that we have what we said before, 135 different Okada events. So then we can start with the processing part. Let's say we have all the ingredients because we have the list of the events. We have also the mathematics because we are going to consider 4 different computational domains. And of course, we have the forecast point or the points of interest along the Spanish coast, in where we are going to calculate wave amplitude for the tsunami to later extract the maximum height and the minimum arrival time for each one. So we start our timer in this moment, and for each forecast point, we are going to obtain the 135 serial times for all of these forecast points. Then, as Jorge mentioned before, we are grouping this forecast point by regions, defining by IGN, and provide them back the alert level based on this simulation. In particular, where we are providing the maximum of the maximum heights, the 90 percentile of the maximum height, and the minimum of the minimums arrival times. So let's try to run the simulation. The main script is quite simple. We have to, it's called main script. We have to pass as argument called master part file, that is a kind of template in which we declare the common parameters for all the simulation, such as the simulation time, for example, that in this case is 4 hours simulation time, the variables to save, and other intrinsic parameters of the numerical model. Indeed, we are going to incorporate the lines of the lines list of events provided by IGN in order to create the individual part file different for each simulation. Okay, we pass also as argument the domain and the resolution. Okay, I wanted to say that this process is automatic. I mean, we receive the list of the events, and when we receive the list, we press the start button to run all the simulations. So here I wanted to show you manually, but the idea finally is that all of this process is automatic. Okay, thinking on the resources, okay, for this demo, I was thinking on launch this, let's say, full script based on the reservation that Marconi 100 has for us. That was 68 nodes. So 68 nodes with 4 GPUs per node, we have enough resources to be able to run 2 sets of 135 simulations simultaneously. So we decided at first to run these 2 jobs at the same time, because this first job occupy the 34 nodes and the other 34 nodes for the second one. Then we expect to be finished this first domain in 1 minute. Then the second domain, the high resolution domain of 1/8 arc-minute resolution, spend a bit long time, around 7 minutes. But in the while, we can solve the intermediate resolution of Gulf of Cadiz, including Canarias, and Gulf of Cadiz, including the northern part. So we expect to have all the results in less than 8 minutes. Okay, so let's see. Let's put our timer at 0. And the idea is I'm going to to launch this full script in the sense of we are going to submit one job per domain and resolution. Okay, so the idea was to run this main full script. As you can see here, the first step is to submit a job with 135 simulation. Then the second one, that is Gulf of Cadiz at 1.8. Then we submit the Gulf of Cadiz including Canary Island with the intermediate resolution, and finally we submit the Gulf of Cadiz including the northern part, okay, as the fourth job. Okay, let's wait for a while, and we are going to check the queue. As you can see here, okay, if we had the reservation for all the nodes, two of these jobs, in particular this one and this one, were running. Let me, I don't know if we should stop these jobs and try to apply the suggestion by Piero. I don't know if I can cancel better to try to do what's the last email is. Okay, let me add this to complete the reservation. So I don't know, it's, sorry for that. I'm going to cancel and start again. Okay, so let me, yeah, I have received an email saying that I have canceled the jobs, and I'm going to modify with the suggestion of Piero the jobs. Yes, this is the job generated to afford with the 135 simulations. Let me add this. Reservation equal res PD2, I think is correct, and the suggestion is to use QoS res. Let's try to run again this job. Okay, cross your finger, please, and I'm going to run again the same script. The same script is processing all the jobs again. Sorry? Yes.
Do you see in the what you're typing in the screen, Carlos? Is moving or not?
Sorry?
What we are seeing is what you're actually writing.
Now it seems to be okay. Okay, I'm going to check the queue status just in a while, and I think everything goes well now. We are waiting for the queue status. Okay.
If it's working, that is computing on the flight and solving the problems on the flight.
The time. Okay. Now, yes. Okay. Thank you, Piero, for your suggestion. As you can see here, we have the first two jobs running, status running. The first one is the Atlantic in 1.5 arc-minute resolution, and the other one is the high resolution domain with Gulf of Cadiz at 1/8 arc-minute resolution. So we expect to be solved, or we ended the first job of the Atlantic is in less than 1 minute. As you can see here, this is a really live demo because we have received an email saying that the first job has ended in 1 minute and 3 seconds. So we can proceed with the post-processing. This would be automatically but we can proceed with the post-processing of this first set of results. We check the queue, all jobs are finished, and we provide all the analysis result of this 135 simulation. We provide this table to IGN with the result desirable for that. As you can see here, we group the forecast point in regions, and we provide maximum of the maximum height, maximum of the percentile 90 of the maximum height, and the minimum arrival time for each region. Okay? And also, as you can read here, we have also generated a map, an interactive map with the results. I'm going to try to download to local. Okay, so we go to the results, and it could be here. Here it is. It's a map. I'm going to download. Okay, I have to overwrite the one I have in the desktop, and I'm going to show you the first one, that is this kind of map. Okay, so we see here. All of the forecast points classified by colors in relation with the maximum of the maximum height, and we also can go zoom in each point. We have a lot of information about that. We have the maximum height for this forecast point, the mean, the standard deviation, and the 90 percentile. Also, we have the identifier of the event in which we reach this maximum height, and also the minimum of the minimum arrival time for all the simulation, and also the source, the identifier of the event in which we obtain this minimum arrival time. So also, as you can see here, classified by zone, we can also color this region according to the table we have seen there. Okay, so we color all the regions in this map according to this the table we are obtaining in this first set. Remember that we are in less. I'm going to check again the queue. Okay, this of Gulf of Cadiz is still running, and Gulf of Cadiz with Canary Island at 1/4 arc-mean resolution. It's nearly to end. Okay. Here you can see an email that say that this particular job has ended in 3.15 seconds. Okay, so we are also can also proceed with the post-processing of this event, that is Gulf of Cadiz, including Canary Island, at 1/4 resolution. Okay, and in the same way, we obtain a table with the results according to the region we are going to analyze. Okay, we have applied this calculation, the same, maximum height, maximum of 90 percentile, and minimum arrival time for this region. And also we can generate a kind of map with this. I can show you. Okay. Here we restrict our domain to the points of this region, Gulf of Cadiz, including Canary Island, and we obtain the same information but with higher resolution than the first one. Okay, we are now at 5 minutes since we start the submitting jobs. Okay, also we obtain this color by forecast point and also by zones. Okay, and these color regions are based on the table that we have shown before. Okay, we can check the status of the queue again, and as you can see, we have almost 7 minutes for the high resolution level domain, and the last set of 135 simulation that are still running. Okay, we can wait for maybe the first one is nearly to end now. Okay, we have more or less in 6 minutes. And the powerful of all of this is the possibility to have this amount of resource to perform simultaneously simulation is the main thing of all of that. And here you can see that the high resolution domain in the Gulf of Cadiz at 1/8 has ended in less than 7 minutes. And also the last one, the Gulf of Cadiz, including the north part, has ended in less than 3 minutes. So we can stop. Yeah, we can stop now our timer because we have performed the 540 simulation in less than 7 minutes, and we are able to go updating the results as the simulation of each domain is ending. Okay, so here we can post-processing the Gulf of Cadiz with the northern part and obtain this table, and also that is the final domain, which is the high resolution domain, generating this table and also the interactive map. Okay, let me download these two maps. Cadiz at 1/8. Okay, and this one. Okay, so here we have one corresponding to the Gulf of Cadiz into the northern part with a resolution of 1/4 arc minute, and also the high resolution map corresponding to the small region but high resolution that is the Gulf of Cadiz. Okay, so we have here the first one, that is Atlantic in a low resolution, intermediate resolution, that are this domain with the Canary Island, this domain with the northern part, and also the high resolution domain, including only this part of the Gulf of Cadiz. So in less than 7 minutes, we have the results of these 4 sets of 135 simulations together and simultaneously run by 2x2 sets. And it's all from my side.
Okay, thank you. Oh, thank you, Carlos. Wait a minute.
Thank you, Carlos.
Wait.
I'm going to stop sharing.
Okay, thank you. Do you hear me, Carlos?
Yes.
Okay, so thank you very much, Carlos, for the effort. Thank you very much for being able to to respond to such a critical situation and being able to compute on the flight and to solve the problem on the flight. That was amazing, and I think that we finally fulfilled the objective that we proposed during this live demo. And now I just let's see if there is some questions, some comment that you want to do. We have a 10 minutes delay due to this technical problem, but I mean, at the end, with a happy ending. Thank you, Carlos, and thank you, Piero, and all the guys at Chineke for trying to solve that's all on the flight. Thank you. So please, if there's any questions, or yeah, please, Stefano, you can open your mic.
Yeah, congrats. Good job, Jorge, Carlos, and Piero. Cineca on the other side. Congratulations. Difficult to manage these situations when things are not going perfectly. So really congratulations. Just for the sake of clarity, have you estimated the lead time you have in a situation like this, the lead time for evacuation or for any action? Because you have shown that you perform, let's say, the simulations in 7 minutes or something less, right? Then you should add, I guess, a bit more than 5 minutes before you get the first seismic solution, just order of magnitude. And have you estimated the travel time to the section, to the segment of the coast with the highest threat according to the simulation, just to have an idea of the realistic lead time in this situation? And a second question will be if you can show if there has been a gain by increasing the resolution when you pass from, and what's the concrete difference between the different cases when you go to higher resolution. So first one, lead time, and the second one, the resolution. Thanks.
Thank you very much, Stefano. First, I would like to say that we tested everything that everything would go okay, but the only thing we could not test was to do in real time with the dedicated, GPUs for us, because we tested when we were going to the queue, and we tested everything and everything went okay. But the only thing we couldn't test is the thing that went wrong, but fortunately at the end was okay. Now going to your question, Stefano, I think that the good thing here is that you have a first answer, a very quick one. In all the coastal point that you're interested in, let's say 1 minute. So that is pretty fast. Then at the end, you have a response, a refined response in 7 minutes. And the good question, as also wrote in my slide, is, well, it's giving more information or it's useless to do that. We didn't have the time to analyze the result and to see what happened in detail, but there are at least some of these focal points where the level is increased from orange to red. I don't know if it's Carlos looking the result with more detail can say something more. So it may change a little bit the result, but it's something that also was mentioning in my slide. Now it's time to analyze all the results.
Okay, doesn't matter. But Olga, the question is, what is?
Okay, the time.
The time from there to there. Okay.
And then, as I said, the good thing is that we have 1 minute. Okay, 1 minute, a first quick answer, and then the arrival times to the coast. I mean, you have there the arrival times to the focal point. That is much shorter. The arrival time to the coast here is about 1 hour, 55 minutes, 1 hour. So, I mean, for this case, is much better than in the Mediterranean. That it's a completely another case. So, and I was missing the answer. I was going to the second one at the same time. I was answering your second question. That was what happened when we increase the resolution, and I was saying that at least we observed that there are 1 or 2 focal points where the level of alert, in this case, is changing. Okay, Carlos, do you agree with me in that assessment?
Yeah. For example, let's see here the classification by zones. Okay, so we have here the comparison of the areas in yellow and red. When we increase the resolution, maybe these values could change, but the color are the same. But if we go to the high resolution, we observe that we change the yellow area of ChEESE 2, I think, into red. So this means that in this, for example, in this case, we observe different values from the approximation of the general or the low resolution domain, which classify the region in yellow, and then we have the updating information classified in red. So we observe this thing also by points, but in the case of region, we also may observe these changes, small but changes at the end.
Perhaps it's not changing the final whole alert level in the segment, but as I said, we haven't looked at it in detail. Okay. Thank you very much for your question, Stefano. And I see Diego's hand raised. Please, Diego.
Yeah, my question is related to the one that Stefano just asked, but in the opposite direction. If you lower resolution, do you see significant changes in your solution or not? Because you could be overcomputing. You know what I mean? Yeah. And together with that one, I was a little confused because there was only a few instances in which you provided the resolution in terms of a quarter or 1/8 arc minute, but in general you were talking about the number of nodes that you were resolving, but it's hard to figure out the resolution that's being used. So it wasn't very clear to me. And then you were talking about areas of high resolution and areas of low resolution. Are those associated with regions of deep water and shallow water, or how do you determine those? And then my other question is, my understanding is that you were also computing inundation at the same time, even though you were only interested in the maximum amplitude at the focal point, right? So kind of three questions there. Yeah. One is whether you're over-converged in the problem, and you could speed up the calculations by using less resolution with pretty much little impact on your final result. Second is exactly, what is the resolution in deep water and shallow water? And the third is just to confirm that you're also computing inundation, even if you're not paying attention to it.
Yeah, I mean, I think it's as we start with the Atlantic domain, the whole domain, with 30 arc-second resolution, and we're computing in 1 minute. It's something like say it's worth it to do in less time and with a course of resolution. That is the first question. If you agree that one minute it's okay, then the rest is something like it's forced, because if we don't want more resolution, then we are done. In 1 minute we are done. Because what we are doing next is going to a reduce domain, increase in resolution. So if the point is that we don't need to increase resolution, 1 minute we are done. If we do not agree on that, then okay, we try to do higher resolution simulation to see if we improve our assessment. And I mean, in some sense, we are producing alert level more accurate. And then we move to other domains that are contained in the larger one, moving to this 30-second resolution to 15-second resolution for the northern Spain and the Canary Island, and finally going to a smaller domain in the Gulf of Cadiz, going to 1/8 of arc minute. So in some sense, I would say that it's more or less fixed, because I mean 1 minute is okay. If you don't want to find a resolution, you stop there. In 1 minute you are done. If you want to test if you could do better, then you look for reducing the domain, increasing the resolution, and that's the idea. So okay, so regarding if we are doing inundation, Tsunami is always doing inundation, but with these resolutions, I mean, make no sense to look at the inundation itself. Okay, so if you want to look at the inundation, then you should perform nested meshes and having final resolution in the coast. But we are not doing that here, of course. We are just computing fast. Computing fast means that a single resolution for the whole domain, not looking at the inundation. And I think in some sense that was also responding to your other question, because of the decreasing the resolution. In some sense, I think it with the computational power provided by the single GPU, this resolution it's like the one we must use to be in a compromise between accuracy and time to solution. I don't know if you more or less agree with my answer, Diego.
Yeah, I do. I was just wondering, for instance, in a situation where you don't have as many computational resources available, whether computing a lower resolution has a big penalty on your solution or not, because it may be that it doesn't. you know, and that will provide an.
You must also think that this is not the final setup. This is the setup that we designed with the AGN guys, and that we thought that it's reasonable, but probably we see that it's not worth it to do several things or whatever. Now when we analyze the results, because as I said, it's the very first time we do, and we didn't have the time to analyze the result. And essentially what we did was to check everything was working, and today running on the fly. And that's also, I mean, more analysis is required, and then we will have you know, more precise answer to this kind of questions.
Yeah. Okay. No, I see.
Thank you very much, Diego. And also see Nico's hand raised.
Thank you, Jorge. Congratulations on the demo. Very interesting. I would just like to ask one question related to the idea of initializing the simulations of what information you're waiting for. Are you just waiting for the magnitude, epicenter, and focal depth, and you get the rest of the parameters from the database? Or do you wait for the moment tensor as well to get some of the parameters for that?
Yes, please continue.
The second question is only related to if you apply weights to the height that we compute with 90% probability. If also all time series have equal weights, or you weight them differently.
So sorry, I didn't. No, so can you repeat the second one, please?
In the table, you compute the max of the max, but also the 90th percentile. So I'm just asking if you apply weights for that, or all solutions have equal weights.
Okay, yeah, very good. Well, for the first question, what we weight? Well, if by we mean you mean we, the code developers, we are expecting to receive the Okada parameters. But that is not probably your question. If by we you're expecting the IGN, as I think that Beatriz was explaining, really what they have is an estimation of the location and the magnitude. With that information, they go to the data set, the database, and they get the fault that is there, and extract this information, that is the strike, deep, rake, the depth, length, width, and the slip. I mean, some of them, length, width, and slip, you know, you get from the magnitude for this relationship, and so on. But from our side, we're expecting to have this list that you saw, this list of I think that is 9 parameters of the Okada model. As I said, the location, strike, deep, break, depth, length, width, and slip. But what they are doing at IGN, and I think that you do, you know, NGV also, is to have an estimation of magnitude and location, and with that you go to the database and obtain from that database the rest of the parameters, and then you send to us, to the guys that are going to compute, and we use all these parameters. And your second question was about the how you say, the weight of this. We are not using any weight. That the main, I mean, here we are not giving a probability to each event. All events are the same, and I mean there is no need, and it's not necessary to give a weight, because really what we're doing is, okay, we have some variability, we don't know, we change a little bit the parameters, and we take in this variability, you know, the maximum, or whatever, a certain value for estimating the Hassler, and that is a maximum of the maximum of the percentile 19. But no weight is given, no probability is given to the event.
Okay, thank you very much. Thank you.
Thank you, Nikos, for your question. Okay, I don't see any more hands raised. Is any other questions, comments you want to
Jorge,
do?
there is my hand, Andrei.
Thank you, Andrei. Please go ahead. Go ahead.
So my question is about what's your approach regarding the, say, the last mile problem in the forecasting? So because you predict the wave heights offshore on the forecast points, but actually people are living on the coast. So we're interested in the, say, the level, water level, like at the coast. So what's your strategy? How you make this step from the offshore positions to the prediction, say,
Okay.
the wave height on the coast?
Okay, really, that's a question the IGN guys can answer, and also Carlos can show the what we do. I mean, in some sense, we have the what happened in these focal points. With that weight height, we have we produce an alert level. Okay. So depending, and that was in the Carlos. Can you show? Can you share and show one of this figure? And attending to the height that you get in this for this segment, you produce an alert level. So after that, something that perhaps when we didn't explain clear enough. After that, and I said that the final objective was to produce alert levels. So we are using this computation, we are aggregating in some sense the results, we are providing the maximum of maximum, for example, and with that we are producing, you are generating an alert level. That in some sense, I mean, it's also something that now we can refine by doing what, for example, okay, now we continue the simulation, we perform high resolution simulation with a very fine coastal inundation and see what these levels in the forecast point represent in the inundation area. And you know, we go, as you say, to this last mile that is the at the end the very important thing for civil protection and for the people involved. Probably Carlos, you hearing me or not? Carlos, are you there? Yeah. Do you have any figure that can show that? I don't know, because I didn't print my presentation. If it, but I mean, more or less, it that I think that answer your question, isn't it, Andre? That
Yes, what you said, that you are kind of trying to gather statistics of what is the correspondence between this alert level as defined offshore and the inundation simulated at much higher resolution. So kind of, if you
what I was saying, that also that the table with you know, the figures that Carlos was showing was the, you know, the numbers for this maximum water height, okay, in the focal points. But at the end, the final product, and what we are seeing in the figure, where the in this green, yellow, and red, were the final alert levels that were I mean, communicated to civil protection and the population, and that is the final product.
Yeah, for the moment.
Yeah, please, Bea, go ahead.
Yeah, for the moment, to compute to estimate the maximum height close to the coast, we are using the simple model using the green coefficient. We are not running inundation simulations.
Please, Juanbi, can you go ahead?
Yes, thank you. No, it's what Bea has just explained now. And well, now that I'm talking, I would like to comment also on some other questions that have been raised before. One is about the resolution. Well, probably with this demo, we are not going to be able to know if it's worth it to have higher resolutions or not, because this is one case and perhaps other cases can be different. What we have concluded with a broader set of tests at IGN is that at least we need 1/4 of minute of arc of resolution to be able to model some heights that have been present in some historical events. So in this case, maybe there is no much difference between the first the first run of the simulation with 1/2 of the resolution, and the other one with 1/8. But in other cases, it would be so. In that cases, it's worth it, and perhaps in this one, it isn't. What we do finally, as you have explained, is to issue an alert levels for each zone, and we produce a message only if the results are different from the previous one. So in this case, could be that the first message is enough, and we don't issue more alert messages. But in other cases, it could be that the third run of the simulation with a higher resolution raises another alert message to our civil protection. And also about the lead time that Stefano were commenting. In these cases, we have some minutes lead time. We are using only the location and the magnitude of the event. We are not using the focal mechanism, as we have been talking. What we do is with the location, we select the fault that is closer to that location, and we assume that the mechanism is the one that is in our fault database, and with the magnitude that can be an MW proxy, we estimate the extent, the area of the rupture of the fault rupture. So this we do it definitely in less than 5 minutes. In cases like this one with the epicenter in this area. So we have 5 minutes for detecting the event, probably less than 5 minutes, around 3 minutes. And then, as we have seen, 7 minutes in this case to do the higher resolution simulation. So we can say about 13 minutes. And in this area, in the Gulf of Cadiz area, the arrival time were about 30 minutes or more, so we have about 15 minutes at least lead time.
Thank you for your clarification. Here I see in the chat a question by Arnau Fall, and is saying that it's mainly addressed to the IGN. Is there any official mechanism to coordinate alerts with Portuguese and Moroccan authorities? Probably also Fernando Carrillo may answer, or Juan Vicente.
No, it isn't right now. The only thing that we exchange seismic and sea level data in real time. But as far as I know, there is no really a coordination between the civil protection authorities about this. The alert messages. I don't know if Fernando.
Yeah, I can add a few words on this. I'm not also aware of any coordination between the civil protections, but between ourselves, when there could be an alarm. The information is sent to IGN as the National Tsunami Warning Center for Spain, as well as for the civil protection, and the same to Morocco, to civil protection and to the National Warning Center. But this is the alarms that we produce.
Thank you, Fernando. I say that it's good that we have here our colleagues from Portugal, but unfortunately we don't have a representative from Morocco. And I think that this setup and this problem is quite interesting for all of us, from Morocco, from Spain, and from Portugal. Here is say Jose Manuel, please, from GREA. You want to? I see your hand raised.
Hi.
Hi.
Hi. Can you hear me?
Yeah, sure.
Okay. Nice to see you guys. And I have a simple question regarding with the computing resources. Sorry, but I lose the first part of the presentation because I was outside my base. And what kind of resources regarding with the computing can you use for this kind of? I mean, it's always the same, but like the ChEESE Center of. You are going to use another computing center, for example, in Barcelona. Or what is the ability of this kind of center for a real situation? I mean in terms of times, you know.
Yeah, here the answer should come from any of these tier 0 centers, as here in Spain, the Barcelona Supercomputing, or in Italy, the ChEESE. I mean, what we have proven today is that once we have a mechanism for doing that, in the case of an event like that happens, then we are able to communicate with this computing center. I mean, I think that it's the IGN in Spain. The natural thing should be Barcelona Supercomputing Center. So to have some resources that should be, prepared in advance, to be able to communicate to the Barcelona Supercomputing Center, as I mentioned, as we in the Aristotle project do between INGV in Rome and the University of Malaga. There is a communication, there is some kind of resources available to run this. Once we are able to do that, and it's more I think some kind of political question than scientific or technological question, we are ready to do something that we have seen today, because the IGN is not going to buy 135 GPUs. Okay, and but I mean, to your particular question and to answer it, it should be someone from ChEESE or from the Barcelona Supercomputing in Italy. Well, in Italy, I don't know if now INGV needs ChEESE, because they are having quite a few GPUs already, and they have already a quite huge potential to compute. But I mean, we are ready to do that, and as I said, this is something that's feasible today, and the challenge is with our friends from INGV are with the collaboration of the Tsunami team in ChEESE are trying to do with the PTF. Yeah. Okay, I've seen some more hands raised, but I don't know if they are still raised and we didn't put down, because I see Diego again, but I don't know if you want to. And I think that also Juanbi has his hand raised.
No, I'm
someone
okay.
else.
I'm finished.
Okay, so, Diego, you're okay too?
Yeah, I actually have a couple of quick remarks here. One regarding of something that was previously mentioned about the coordination with Morocco. I don't know exactly who the coordinating point of contact would be in Morocco, but I know that Morocco has reached to us recently, to NOAA, because they had the intention of establish a tsunami warning system in the country. And so someone that has reached, it was not from the scientific side, it was someone from the government. It has been routed to us. We got back to them, but they haven't replied. So just for you guys, it would make more sense that they coordinate with you, but just so that you know that there's an intention from the Moroccan government to develop that system now. And then the other question was regarding the last questions on whether the setup at the supercomputer centers would be operationally feasible or not. That was actually the reason why I asked the question about the computational resources earlier, because a few years ago, we tried to set up a similar type of environment with NCEP, the Weather Service Supercomputer Center, and the latency in the data transmission and the cost of having the number of dedicated nodes there for us to compute that were only really used 2 or 3 times a year was exceedingly expensive. So the final solution was actually, that was when we moved to the GPUs and run in-house at the warning centers, which seemed to be a much more appropriate solution, let's say, for the warning centers. Running at this supercomputer center, at least here in the US, and running at NSEM proved kind of not streamlined for the type of application that Tsunami had. Because in Tsunami, you need to have, when the earthquake happens, you need to have all the nodes available to you within a second, and then you need the information transferred to you immediately, and they were just not set up for that type of application. I don't know if it's the same at other centers or not, but we ended up doing things locally in-house at the warning centers and purchasing hardware for that purpose.
Okay. So, yeah, thank you, Diego. We have now that probably can clarify that, but the idea is not to have dedicated resources all the year. I mean, is that you stop them when this happens, and taking into account that you need, you know, like 5 minutes, 7 minutes, I don't know, to have a good determination of the magnitude and the location. You have that time to, at the same time, communicate with the supercomputing center, stop the computation at you know, some resources, and then use that resources. Not obviously to have them reserved all year around for a tsunami that will happen in 20 years. Okay. So, but I saw Arnau full hands raised, please. Arnau.
Jorge. Yeah, I can comment on that because this is a very important point. As you know, ChEESE is a project, and the purpose that we have is to test all these potential services in an operational environment that we have done very successfully, by the way, today. No. But now it's clear that there is one step more, and we need to push for this urgent computing service. But this is a bit more complicated in the sense that it needs some formal arrangements and agreements between supercomputing centers or EuroHPC in the future in the case of Europe, and the people or the institutions that are providing the service. No? So it goes a little bit beyond of the scope of the project, but it's something that we have on mind and that we are pushing forward on this urgent computing service, not only for tsunamis, but for several other natural hazards. No? So we just wanted to comment on this.
Yeah, thank you. We have talked about that in ChEESE project, of course, and Tommaso, I don't know, perhaps can also comment on that because he had been on charge of these services thing. I don't know if he's still around, but he could also give his point of view if he's still around. If not, we have here Victor Huérfano, please, from Puerto Rico, please.
Yeah, thank you, Jorge, and congratulations. It's a very tremendous program and very, very nice. Thank you. I have two questions, Jorge. One is, as you know, the seismologists are still working to provide as soon as possible the source, the focal mechanisms and the inversion of different kinds. So, and in addition, most of the networks have tide gauges all along the coast. So my question is, in both cases, if you can't obtain as soon as possible the solution, or if you have tide gauges data, you can't use that data in your on-the-fly code, or you need to run again from the very beginning?
Well, it's something that we don't have as today, we don't have in the code. It's something that in the case of the NEAM region, I think that make not sense because we don't have time to do that. Once the tsunami wave have arrived to these tide gauges, all is happening. So make no sense to develop this kind of tools from the Mediterranean of the Atlantic Ocean in the case of as a sample of today. But perhaps it's something interesting for doing in the Pacific, and it's something that an idea that we could try to investigate, but we have not done yet. We are not including. But I don't know if Manolo is around. I don't know if he's around. He can give an answer to that. I don't know. I know that he was connected at the beginning, but I don't know if he's still here. But as I said, we have not yet in the code, and it's something that we could think for application in the Pacific, for example, in big event coming from Japan, for example. Okay. So any more questions from the audience? I see no more hands raised. So well. were a bit longer than expected, but I think that the discussion was quite exciting and quite fruitful. So I'm very happy to see your interest, and also to see how we were able to solve the problem on the flight. Really, we were really nervous about how this was going to go on, and the very bad news that could happen happened, but at the end we solved it. So if there is no more questions, I would like to thank you all for the interest, and we have recorded the thing. We will send you a link for the recording if you want, or you want to share, and that's it. Thank you very much, you all, for being here. If you have no more comments for your side or from the IGN guys, Juanbi, Bea, some more comments.
Only saying thank you to Seneca, Carlos, Piero. Thank you for the demo.
Carlos, are you still alive or not?
I'm still nervous.
Still alive? Okay, thank you very much. Thank you for your quick response and action, and thank you for being here.
Thank you.
Thank you to everyone.
Thank you.
Thank you for your question, and thank you for your comment.
Thank you very much.